So anyway, let me first put on sort of my scientist's hat, and I will say a bit about one way that you can think about structure and geometry in the scientific research that I'm doing, but without being kind of too self-reflective about the questions that Michael has introduced initially, and then I will try to give a bit of reflection on that. But as mentioned, I'm here at EPFL. My laboratory is about 200 meters from here down in the basement, so we have very stable conditions for our apparatus. We use laser pulses, light, to both investigate materials and to control them, to change them, to affect their structure, to understand why certain structures form and look at that in real time. And I wanted to give sort of two small bits of input on how important in different ways geometry, structure, symmetry is to the type of research that I'm doing. And one of them is in terms of how we explain the things that we see in different materials. So I bring up to you here two pictures. On the left, we see some graphite, which is also exhibited in the pavilions. On the right, we have diamond. And now, if you would be a kind of naive reductionist, you would look at the material and ask, well, what is it made of? What is the atom? And in both cases, we say that the atom here is actually carbon. It's actually exactly the same. However, the two materials couldn't be more different, both electrical, magnetic, optical, mechanical properties, everything here is different, right? So clearly the answer to understanding a system is not just to look at its constituents, but to also look at their interplay. And it's not something we can understand by just looking at 2 or 3 carbon atoms. You really have to go into the kind of many-body limit, as it's called. And on the left, the graphite, we have a structure that looks like that. We have sort of layered hexagons. And on the right, we have a structure that is, not that two-dimensional in that sense, but more intertwined. And this difference in structure is really what is used as an explanation for why these two are so different. So this is one way to think about why it's so important to actually think about structure, to investigate structure, to look at materials, and why it can be a promising route, and this is what we are doing in my laboratory, to try to change the properties of matter by not replacing the atoms, but by actually just trying to sort of slightly tweak the structure that you have. The second input I want to give is that I actually think that thinking about geometry, symmetry, is a way that can help you predict things, learn things, understand things, that in a way is, it works very much together with other types of mathematics equations, the usual things that we have, Newton's equations, Schrödinger's equations, and so on. But it can even sometimes tell you things without having to really revert to those directly. And I'd like to give a small example from the kind of thing that interests me most, which is the interaction between light and matter. So if you have some kind of object and you send light at it, you don't know what's in there. One thing that can happen is that some light comes out at twice the frequency. In fact, unfortunately, this is one of these modern laser pointers that is not a laser pointer, but if you have a green laser pointer, there's a high likelihood that inside there's actually first an infrared laser that then goes to a crystal and gets doubled. You get double the frequency and that becomes green. And in order for a crystal to double light, to have an oscillation and get the square of it out, you actually have to have that crystal break a certain symmetry. So that crystal looks like this. It's called having inversion symmetry or point symmetry. You can pick a specific point in that crystal, and that doesn't work, but it's fine. You just pick, let's say, the point in the middle of the square. You can apply a point symmetry operation. You can invert things around that point, and you will get the same thing. And this is why, if you send in this red light, it won't be able to say, should I be squared in the upwards direction or in the downwards direction? So in a way, both things happen, they cancel out, so nothing at all happens. Whereas if you have a different kind of crystal, one like this, where this symmetry does not exist, the orientation of that particular geometry and shape will tell you, oh, now I can actually create double the frequency. And I've not had to revert to quantum mechanics or anything here, right? This is really just looking at what kind of symmetries you have and what could be possible from a symmetry or not. It has actually by now become a situation where you tend to send light at something, and if you get twice the frequency out, you say, oh, the symmetry must be broken. So we sort of inverted the logic of it a bit. So these are sort of two small, let's say, in the language of science type of inputs that I want to give here, I want to kind of add one more thing to the overall tone of the discussion. You were asking earlier, you know, is scientific visualization art? Is geometry a way to describe nature, or is it the other way around? For me, I'm very much on Wittgenstein's kind of line on these things and saying that the meaning of a word or of a phrase is its use. So if we call something art, right, that plays a role, that has a meaning, that we as humans in the community somehow ascribe. And I think it's very important for me when I have a discussion about this, and it actually makes it more interesting, less interesting for me, that it's not that there is a truth on that question somewhere out there in the forest and we have to find it, right? We are the ones that decide ultimately how we use the word art. And I don't think it's arbitrary. I think it's an important process, and I think this kind of discussion is part of that process. So I'm looking forward to that.